So the last part of section 6.3 is finding inverses. So we had talked yesterday about the inverse properties of these functions. And we talked yesterday about how log base b of b to the x power equals x and log b to the log base b of x equals x. All of that stuff, we talked about those properties. Now those are introducing the idea of exponentiating and taking the log of both sides. You remember way back when we talked about solving inverses or finding inverses, the first thing that you do is you switch the numbers, or you switch the x and the y. When you switch the x and the y, then you solve for y. The issue that we have with logs and exponents is that we don't know how to solve for y right now. So that's what we're going to pay attention to. Okay? So let's say we've got the equation y equals 6 to the x power. Okay? So if we have something that looks like this, y equals 6 to the x power. If I'm asking you to find the inverse of that equation, the first thing that you have to realize is that this is an exponential equation. So this thing right here is an exponential equation, which means that if I'm taking the inverse of this thing, what kind of equation is it going to turn into after I take the inverse? It's going to turn into a log equation. So this will be a log equation when everything is said and done. If it's not a log equation, then that means that I have not done the inverse correctly, because the inverse of exponential equations are log equations and vice versa. Okay? So that's something that you have to pay attention to. The first step is the same as what we did last time for the first step of finding inverses, and that is switch your x and your y. So it's x equals 6 to the y power. Absolutely nothing is going to change here. Nothing. Okay? Now we have to find solve for y. This is the hard part, because as of right now, we don't know how to get y out of the exponent. Okay? So this is where I always say, ask the question, what's happening? So right now, what's happening is that there is an exponential or an exponent that we need to get out of the exponent. We need to get that y from the exponent down. How do you undo an exponent? By a log. So that means what we're going to have to do is we are going to have to use the inverse property of logs to cancel out the exponent. Okay? So the big thing that you have to pay attention to is that the bases need to be the same. So right here, I can see that I'm going to need to take the log of both sides. I'm going to need to take the log. But what you really have to pay attention to, and I'm going to put this in parentheses, you need to pay attention to the base. If you don't use the same base that it already exists in the problem, you will do absolutely nothing for the problem. So if I'm not using log base 6, this problem does absolutely nothing. So if you think of an equation where I ask you to solve x equals 5y, like this, you would divide by 5 to solve for y here, right? If you divided by 6, nothing would happen. If you divided by 2, nothing would happen. If you don't divide by the important number, it doesn't make a difference. So if we don't take the log of the important number, nothing happens. Okay? So what this looks like is we are going to take the log of both sides. Now I'm going to be a little obnoxious about this for the first one. But when we take the log of both sides, we are taking log base 6 of both sides. Okay? Now what I wrote that really big so that you knew it has to happen to both sides, because I can't just do it to one side and hope that everything works out. So I have to take the log of both sides, and then everything else will stay the exact same. So notice that the parts that are in black stayed the same. They did not change at all, right? The x equals 6y is still there. Now I've just taken the log of both sides. And notice how it's still consistent, right? Each side of the equation is still equal because the only thing I introduced on both sides of the equation. The whole idea behind this now is based on the inverse properties that we talked about yesterday, is that when I take the log base something of something to a power, as long as these two bases are the same, they cancel and go away. So that means that this will turn into log base 6 of x equals y, and there is my inverse function. Okay? Hopefully this makes sense. It is going to be something that takes a little bit of time for you to practice, though. It's going to take a little bit of time for you to understand how to take logs, how to take inverses, and how to use those things because it's new. It's something that you haven't really done before. Okay? Now that's one half of this. When you start with an exponential equation, you take the log of both sides and you're done. The other option is you can start with a log on both sides, or a log equation, and then you're going to have to do something called exponentiating. And some people have a really hard time with exponentiating, so I'm just going to make sure that we talk about it and we make sure we understand what's going on. So let's say that we've got y equals ln of x plus 3. Now, first off, people do not like ln, right? They don't like ln. The reason they don't like ln is because it doesn't look like log-based something. If this really makes you sad, if this is something that you really don't like, then you can put this as y equals log base e to the x plus 3. If that's something you want to do that. I don't care. It doesn't change anything. So if this makes you happier, do that. If it doesn't make you happy, that's fine. Okay? ln and log base e are the exact same thing. So right now, the issue is I've got a log in the equation, which means that I need to get rid of the log in the equation. In order to get rid of logs, you use exponents. Okay? Now this is going to introduce the idea of something called exponentiating. So you are going to exponentiate, which this is different than squaring both sides, or cubing both sides, or taking both sides to the 5th power, or square rooting both sides. It's different. Okay? What we are going to do is we're going to pay attention to whatever the base is here. What is the base on ln? E. E is the base, which means that we are now going to put a big E on both sides of the equation. Okay, whatever the base is, you put a big one of those on both sides of the equation. So what I'm going to do is I'm going to put a big E on both sides of the equation. And then actually, hang on, I should change this first. Give me 1 second. We're solving for inverse, so we should switch x and y. Right? So switch x and y first. So we're finding the inverse of this equation. Now to solve for y, we need to get rid of the ln. So I am starting by putting a big capital E, okay, or not E, a big E as the base. Then everything in that purple line becomes the exponent in the rest of the equation. Okay, so this becomes e to the x power, and then e to the ln of y plus 3 power. So you'll notice that this is the difference between exponentiating and just raising something to a power. If you said put both sides to the e power, that means raise both sides to the e. Put a big E in the exponent. That's not what we want. We want the e to be the base. Okay? So we want the e to be the base. Now, as we saw yesterday in the inverse properties, anytime you have a base raised to a log, as long as the bases are the same, they will cancel. They'll undo each other. So like 10 to the log base 10 goes away. 4 to the log base 4 goes away. E to the ln goes away. So now this will turn into e to the x equals y plus 3. And now we have a very simple equation where we can solve for y. Right? Because now this is something you do know how to do. You just subtract 3 from both sides. So you end up with e to the x power minus 3 equals y. Any questions on that? Any issues that you can see or anything that looks like it could be a challenge? All right. Yes?
Okay, so this isn't specifically.
Yeah, that's fine.
This, but throughout 6.3, there's like a lot going on.
Mm-hmm.
So are we going to need to like remember it, like remember all the different equations? Like I think we need to know that like E and ln and stuff like that.
So, like, yes and no. But the thing is, the things that you have to remember, or the things that you're asking about remembering, you probably won't ever remember in log form.
Right.
Like, you know, I teach this every year. Every single time I get to logs, I write log base b of 1 equals something, and I put a question mark. And I don't remember what that is off the top of my head. I switch that to exponential form, and say b to the question mark power equals 1, and I go, oh yeah, it's 0. So I don't remember log forms, and I do this for a living. I switch things to exponential form, and that makes things make more sense to me.
Oh,
Does that make sense?
yeah.
So my big thing is I don't really care about the log equations of anything. I care about the exponential form of it because that's what makes more sense to me anyway.
Oh,
So if you know the exponential form, you really don't have to memorize the formula at all.
right.
All right, so this leads us into the graphing section. If nobody else has any questions about inverses and stuff. So we are going to graph logs and exponents. And we already actually talked a little bit about the parent functions for exponents. If you remember, when I said the parent function for an exponent was y equals b to the x power, and I said that the b changes all the time, and then you have your table, right? So that's what we had. Now, if you know how to do that, then you know how to graph logs, and it's no issue at all. But what I'm going to do is I'm going to put both of these side by side so that you can see the differences and you can see the similarities in the same exact line. Okay? So let's start out talking about the parent functions of exponents and compare it to the parent function of a log. So the parent function of an exponent is y equals b to the x power, and this changes. Remember, this was the thing that we had talked about where if b is bigger than 1, this is exponential growth. If b is between 0 and 1, this is exponential decay. You remember we talked about in that section 6.2 quite a bit. So if b is greater than 1, exponential growth. If b is in between 0 and 1, we have exponential decay. Honestly, you don't even need to know that for graphing because the graph will take care of itself. When you are graphing the parent function, you start with your table. You only really need 2 points because you can figure out what's going to happen. When you plug 0 in for x, you will get 1 for y. When you plug 1 in for x, you will get whatever the b value is for y. Right? So you have those parent functions, you have those functions, whatever you need, and you're good. Okay? The next part is the log function. The log function has a parent function of y equals log base b of x. And remember, these two functions are inverses of each other, right? These two functions that we talked about yesterday are inverses of each other, which means what should happen with the x's and the y's? They should flip. So that means that my parent function should now have 1, 0, and then b, 1. And this is exactly the inverse property that we talked about yesterday. Log base b of 1 equals 0. Log base b of b equals 1. That's exactly what's happening here. Okay? Now after that, after you understand those things, there's really not that much different from the stuff that we did over and over and over again through the course of the year. A will still flip this vertically. A will still stretch it and shrink it vertically. H will still move it left and right. K will still move it up and down. There is no b value here because the b value is the thing that determines the h and the k. Or I'm sorry, the growth and decay. All right. So if you understand how to graph exponents, then you understand how to graph logs. We'll go through one of each of them just to make sure that we understand. But I also want you to see a couple of important pieces of information. Okay. So when I'm graphing this, so if I graph the equation for an exponent, I have my 2 points. I have the point 0, 1, and then I have the point 1b. I don't really care where b is. We'll just call that b right there. Now, one thing that is very, very important is you have something called an asymptote. And an asymptote is a line that something will approach, but it will never ever get to. Okay? It's kind of like depositing money in a bank account. You are never going to deposit $0 in a bank account. You could deposit 1 cent in a bank account. You can deposit very little money into a bank account, but you can never deposit 0, right? You can also never deposit negative money into a bank account, right? So as we start to go down, it will never actually get to that value. It'll never get to 0 because you're never going to deposit $0 into a bank account, right? So this is the asymptote of a parent function. The most basic function of all time that deals with exponents is y equals whatever b to the x power. And that means that there's an asymptote at 0, which means that this line is never, ever, ever going to touch or cross 0, and then it's going to have the exponential growth. Right? So the only time you have to worry about the asymptote And I'm going to put this little note down here, that the asymptote shifts up and down with k. Hopefully that makes sense. The asymptote will shift up and down with whatever the k value is. So if I'm shifting the entire graph up 2 units, the asymptote will shift up 2 units. Okay? That's the only thing that should affect it. Flipping it vertically, I guess flipping it vertically would also affect it if it was shifted up already, but really the only thing that affects it too much is the k value. Okay? Because usually we deal with flips first, and then we move it up or down, right? So really the only thing that's going to affect it is the k value. Okay? Logs are inverses of these functions, which means that if I plot these, I should be able to see an image that looks like it's kind of the exact opposite in every way, shape, or form. Which means that instead of growing this way, it will grow this way. Instead of having a horizontal asymptote, it's going to have a vertical asymptote. Okay? So I'm going to plot my points 1, 0. So 1, 0 is right here. And then B1, I don't really care where that is, so we'll call it right there. And then it's going to have a vertical asymptote at 0, because every aspect of an inverse function switches. And then I'm going to start at the asymptote, go out, pick up these 2 points, and go back. Now, what do you think is going to affect the vertical asymptote on this one? Which one? H. H is going to shift it left and right. So H affects the asymptote. Other than that, these 2 things are the exact same. If you know the difference between the table with the parent function, and you know the difference between the asymptote shifting left, right, or up and down, depending on what the function is, nothing changes. A still is vertical, H still left and right, K is still up and down. So let's go through an equation so that we can see what this looks like, and then I will give you guys some time to work on your thing. So let's say that we've got y equals 2 times log base 4 of x minus 1 plus 1. Lots of stuff happening on this one. The first thing to do is identify your parent function. Once you identify your parent function, that gives us our table, and then we just apply all of the things that we need to our table to get our new graph. And then exponents are done the exact same way. Literally, the only thing that's different about the exponential function is that this log doesn't show up. It'd be the same kind of thing as 2 times 4 to the x minus 1 plus 1. It's the same exact type of problem. It's just going to give you a different parent function and a different asymptote, and you're good. All right? So my parent function is going to be y equals log base 4 of x. And then remember, my table went 1, 0, B1. When I plugged in 1, I got 0. When I plugged in B, I got 1. So that's really the only hard part. Everything else is stuff that we've been doing since literally the first week of school. The A value will still affect the same thing it always has. The H value will still affect the same thing it always has. It'll also still be opposite. And then the K value will still affect the up and down the same exact way that it always has. Okay, so the 2 up front, what does that affect? The X column or the Y column? It affects the Y column because it's a vertical stretch or a vertical shrink. So it affects the Y column. So I'm going to take my 2 times my Y value. 0 times 2 is 2. 1 times 2 is 2. Oops, that's not right. 0 times 2 is 0. So 0 times 2 is 0, and 1 times 2 is 2. Now, I like to, because I get confused very easily, I like to cross off the columns that I don't use. I like to keep 2 active columns at a time, and that's it. Okay, then working left to right. I don't have to touch this log base 4 because that is the parent function. So this thing right here, I am not paying attention to 1 bit because that is the parent function, and all of that is already taken care of in those black letters, X and Y, right? So now I have this minus 1 right here. What does that minus 1 do? Moves it to the right. It's opposite. So it's going to take my X values plus 1. So 1 plus 1 is, I can't do simple math. 1 plus 1 is 2, and 4 plus 1 is 5, and then I'm going to cross off the column that I'm not using. Right, and then I have one thing left, and that one last thing that I have is my k value. And what does that k value do? Moves the y column up 1 unit. So that column plus 1, so it's going to be 1 and 3, and I'm done here. What else does that k value affect? The asymptote. Nope, sorry, that doesn't. I was thinking logs, or exponents. Which one affects the asymptote? The one that shifted my graph left or right, or the one that shifted my graph up and down? The one that moved it left and right, right? So really, my asymptote right here, this should shift asymptote 1 unit to the right. So that should shift my asymptote 1 unit to the right. Okay? Now if you want to, we can graph the parent function. Most of you don't care about the parent function. So we'll look at this graph, and now I'll just plot these points. So this is my x column, and this is my y column. I've got the point 2, 1. So 2, 1 is right there, and then I've got the point 5, 3. Right here. And then I've got my asymptote, which we already said shifted 1 unit to the right, so that means that it is through that point now. And then I'm just going to put my points here and draw it. Now, just out of curiosity, if they do ask you the question, what is going to be restricted here, the domain or the range? The domain will be restricted because it can't go any further left than the asymptote. So what would the domain be for this function right here? X is greater than 1. Notice how Olivia did not say x is greater than or equal to 1. It never touches the line, which means that it can't equal 1. Okay? The next part is the range. Is there any restriction with this thing going up and down? Doesn't look like it because it's got arrows at the end of it, right? So this would be all roots. And exponential functions are done the exact same way. The only change is the asymptote. That is the only change at all. Do you guys have any questions or issues or concerns as you sit here and stare at this right now? Anything from today that you'd like to talk or clear up more? Okay, beautiful.